Hello, my name is André Gustavo Carlon, and this is our presentation named Stochastic Optimization for Bayesian Design of Experiments for the MCQ MC 2020 conference. I will start introducing what is optimal experimental design and how we model our experiments. Then I will proceed with the numerical methods that we use for optimization, stochastic gradient descent methods, and proceed with some numerical examples. Well, in optimal experimental design, we are interested in the best setup for an experiment, in the sense that we are trying to find the experimental setup that will provide the best observations. So in this sense, it is both an uncertainty quantification task, because we need to solve inverse problems, and a stochastic optimization task, because we need to maximize some quantity. And different measures of the quality of experiments will result in different optimals, and so we choose to use the expected information gain, as it's already used in many works, the literature. So how do we model our experimental observations? Here we model it as Y. For repetitive experiments and E, we model each observation as the result of a model, here denoted as G, where we have theta as our parameters of interest and psi as our design parameters vector. Now for each repetitive experiment, we have a vector of IID measurement noises that we denote as epsilon, and then we gather all of the observations in a set that we name big Y. Then to incorporate the information that we acquired from the observations into our parameters of interest, we use the Bayes theorem here, where we get a posterior distribution from the observations that we make. Then to measure the efficiency of the experiment, we consider the expected information gain, as previously said, which is the Kublai-Leiber divergence of the posterior with respect to the prior, integrated over the probability of the observing Y. To illustrate these concepts, I am presenting you here some case where we perform some observation, then we have a posterior and a prior, and here I have the integrand of the Kublai-Leiber divergence. So the quantity that we are interested, the Kublai-Leiber divergence here, is the difference between the green area and the red areas. Now if we consider all the possible observations that we can make, then we have a surface like this, and the integral of this surface is the expected information gain that we are trying to maximize. So the optimization problem that we are trying to solve is one of finding this psi star here that maximizes the expected information gain from a design space, big psi here. Also here I am presenting you the integrand of the Kublai-Leiber divergence. When we use some psi star, we can see that we have a larger integral under the solid line, and as a consequence we have a much more concentrated posterior here on the bottom plot. Now, how do we estimate the expected information gain? Well, we use three estimators already known on the literature: the double loop Monte Carlo proposed by Ryan, the Monte Carlo with a Laplace approximation proposed by Long et al., and the double loop Monte Carlo with Laplace-based importance sampling proposed by Beck et al. So what is the double loop Monte Carlo estimator? We get the double loop Monte Carlo estimator when we use Monte Carlo approximation for the expected information gain, and we use another Monte Carlo approximation to approximate the marginal likelihood here. So this estimator has an error decomposition shown by Beck et al. Here as a bias for the m to the minus 1, where we have another contribution on the bias due to some eventual discretization for any method for the solution of the model, and a variance given by these terms here. These constants are shown on this work. Note that the total work of one estimate of this estimator is given by n times m model evaluations. Okay, so the second estimator is the Monte Carlo with Laplace approximation, where to do so we need to get some covariance matrix approximation that we have as the inverse of the Hessian of the negative logarithm of the posterior, and we evaluated at theta n that we sample for each of the Monte Carlo loops here. Note that this estimator has an error decomposition presented here, where we introduce a bias that does not decrease as we increase the sample size, a bias that is fixed of n(e) to the minus 1, and we have a variance that is n to the minus 1, which is smaller than for the double loop Monte Carlo. The cost of this estimator is given by the sigma here. So we need to look at n sigmas. Each sigma requires a Jacobian of the model with respect to theta. So that is the cost of this estimator. In general, to achieve the same error as the double loop Monte Carlo, we need fewer moderate evaluations. So the last estimator that I will present is the double loop Monte Carlo with Laplace-based importance sampling, which is very similar to the double loop Monte Carlo, except that instead of sampling theta star from the prior, we sample theta star from an approximation of the posterior that we get when we use a Gaussian approximation. We use the same sigma as for the Monte Carlo with Laplace to estimate the covariance matrix, and we center this distribution at the maximum a posteriori. So you can see here that the error decomposition, the bias and the variance are very similar to the one of double loop Monte Carlo. The difference here is that due to the reduction of the variance that we get from this Monte Carlo estimator of the marginal likelihood, these constants are much smaller usually. So to achieve the same tolerance of the error, we are required a much smaller m. So we get a smaller cost in general, compensating the cost of building this distribution here for each n. Okay, now that we discussed the estimators for the expected information gain, we need to discuss how to maximize the expected information gain. And to do so, I will introduce this function, which we call the entropic function f, which is the logarithm of the ratio between the likelihood and the evidence, and I will denote as g its gradient. Now, since we proved in this work, Carlon et al. 2020 proposition 1, that for our data model we can commute the expectation and the gradient, we can use g as an estimator of the gradient of the expected information gain to perform optimization. Then next we will derive three estimators for g, one related to each of the expected information gain estimators presented before. Okay, the first one is the one that we get when we use Monte Carlo to approximate the marginal likelihood, just as in the double loop Monte Carlo estimator. The next one is the one that we get when we use Laplace approximation of the posterior, which is given by this equation here. Note that we need sigma, its inverse actually, and the gradient of sigma. However, we don't need any Monte Carlo approximation for this estimator. Here, these double dots denote the double contraction, which is similar to the Frobenius inner product between these two matrices, two tensors actually. Now you can see this work, Carlon et al. 2020 proposition 2, for a detailed proof on how we get this estimator. And last we get this other estimator, which we call the gradient estimator using Monte Carlo with importance sampling, where we use the same Laplace-based importance sampling to estimate the marginal likelihood as in the double loop Monte Carlo with importance sampling. Okay, so now let's discuss the methods that we use for optimization, stochastic gradient descent methods. First, let's discuss what is the full gradient descent method for the maximization of the expected information gain. Remembering that the expectation of f is the expected information gain, here we will be using the true gradient to perform optimization. Now, note that the evaluation of this expectation could be very expensive, not least to estimate its gradient, so instead of doing so, we will use the stochastic gradient descent method, which is much cheaper and consists in using, instead of the gradient of the expected value, we use an unbiased estimator of the true gradient. Note that at each iteration here we will be sampling theta and y independently, and we'll have a noise here due to this not being the true gradient. And to deal with this noise, we will be decreasing the step size each iteration. So here I am illustrating the optimization path for both the full gradient descent in black, where we take the true gradient to perform optimization, and the stochastic gradient descent in blue, where we do have some noisy gradient estimates. However, we are still able to converge, even though we are decreasing the step size. Okay, so to improve the stochastic gradient descent, we can use other techniques like the Polyak-Rupert averaging, where we allow the stochastic gradient descent to take larger steps each iteration and to decrease the step size slowly. and we guarantee the convergence not to the step that we are taking, but to their averages. And we can see here denoted as black dots and arrows the average of the steps that are taken by the stochastic gradient descent, and we can see that they are converging to the optimum in a very well behaved manner. To further improve the convergence of stochastic gradient descent methods, we use Nesterov acceleration here. Nesterov acceleration is a momentum method here, so instead of just going from psi k to psi k plus 1 using the steepest descent or steepest ascent direction here, what we do is we move to z, and then we use information from previous iterations to perform an extra step, as denoted here. Noted that to get this momentum parameter here, we need to set up this parameter q that tunes how much momentum is applied to Nesterov acceleration. Okay, so how does it work? Here I am presenting you some optimization path where we have in red the steepest descent step, and each iteration we are using information from the previous iterations to perform this extra step denoted in blue that we see that is able to get the algorithm to converge faster. To avoid that the Nesterov acceleration moves to unwanted direction, we can use this restart technique that is presented by Odonogwe and Candes, where we just do this check and restart the acceleration whenever it is convenient to do so. Okay, so here I am presenting you convergences for 4 different methods: the stochastic gradient descent method, the stochastic gradient descent method with acceleration, with perfectly tuned acceleration, and with the restart technique. Note that all the methods, they are dominated asymptotically by the same rate of convergence, which is sublinear, which is given by the stochastic gradient descent. However, we are able to get much faster to the asymptotic rate when we use Nesterov acceleration, and specifically when we use the restart technique. We get to the asymptotic region of convergence with 2 orders of magnitude less gradient evaluations. Now let's discuss some numerical examples where we apply the gradient estimators and expected information gain estimators presented so far. Okay, the first example that I will present you is an optimal experimental design with a quadratic model, where we will be using a Gaussian distribution for the priors. We are trying to find psi between -2 and 2. We have a variance for the additive noise of 10 to the -4 and just 1 repetitive experiment. As a stop criterion, we will be using the distance between the point that we are and the optimum, and we used as a tolerance 10 to the -2. So here in this table I am presenting you the average cost in number of gradients over 10 runs to get to the stop criterion for different optimization methods: full gradient descent, stochastic gradient descent, accelerated stochastic gradient descent, and with restart, and different estimators where we use Monte Carlo for the marginal likelihood, Monte Carlo with importance sampling, or the Laplace approximation of the posterior. We can see that the worst case is the full gradient with double loop Monte Carlo, the naive approach, where we need 5 orders of magnitude more gradients on average than when we use the restart accelerated stochastic gradient descent with Laplace approximation. We can see that the bias of the Laplace approximation was not detrimental on the convergence here for this case. Now here I am presenting you optimization paths for the same cost of the Laplace approximation, the Monte Carlo with importance sampling, with different sample sizes. We can see that the accelerated stochastic gradient descent with Laplace and restart was able to go much farther than when we use Monte Carlo importance sampling, due to this estimator having a smaller cost. However, it's interesting to note that even with a sample size of size 1, we are able to get some convergence and go to the direction of the optimum. So our second example is the positioning of a device named a strain gauge that measures strains on a beam that we use to infer the material properties, namely the shear modulus and the Young modulus of this beam. So how do we model our experiment? in the optimal experimental design sense. Well, substituting the position of the strain gauge here, x1 and x2 by xi1, xi2, optimization parameters, and the parameters of interest, which are the Young modulus and the Sharp modulus by θ1 and θ2, we get this model, which is the strains that we measure, given by this equation here. We will be testing some different setups for the prior information that we have to see how the optimal experimental design methodology that we develop performs, and how the expected information gain changes in these cases. So here is the first case where we have kind of equilibrated information a priori about the Young modulus and the Sharp modulus. We see that we converge to this region here. I am presenting you here in this contour the expected information gain. We can see that it has some symmetry on the x and y axis, right? On the second case, I am assuming that we have less information a priori about the Young modulus, and we can see that the contour of the expected information gain changes. And now we have an optimum here at the center of the beam where we can get more information about the Young modulus. Similarly, if we assume that we have less information about the Sharp modulus at the start, we converge to this other situation here where we go to the supports. Now that on the supports you get more information about the Sharp modulus. So here I am presenting you some posterior distribution after optimization in blue, before optimization in red, and the prior distribution in gray. We can see that for the starting point here, we didn't acquire much information, neither about E on this axis, neither about G on this axis. However, as we perform optimization, we get to this point here where we are actually having a much more concentrated posterior. Now on the second case, where we have much more information a priori about G, then we converge to a situation where we learn more about E, as expected. So we can see that we have more concentrated posteriors on this axis than in the red in comparison. And similarly to the third case, we are learning more about the Sharp modulus G here. So our last example is an electrical impedance tomography experiment where we are trying to find the currents to be imposed on electrodes on the boundary of a composite laminate material to try to infer from observation of the potentials on the electrodes the angles of the plies of this composite laminate. So here we have the optimal experimental design setup. We have the experiment observations given by the potentials at the electrodes. Note that here we are using this index h to denote the dependency of this solution on some discretization parameter h that we use for finite element method. We have NEL electrodes. We are trying to find the current to be imposed on some selected electrodes where we are normalizing this current between -1 and 1. We are assuming uniform distribution for the parameters of interest, which are the angles of the plies of the composite laminate, and we have an observation noise which is of variance 100, which we chose to be around 5% of the currents that we measure. To solve this problem, we are focusing only on using the accelerated stochastic gradient descent with restart and the Laplace approximation, given that is the method that performed better on the last experiments. So how do we get these potentials at the electrodes? First, we need to define some conductivity tensor where we input these angles of the plies, and then we need to solve the following variational problem, which is one of finding the potentials on the body and on the electrodes that satisfy the following partial differential equation for all test functions v here. Note that we use finite element method with discretization parameter h. So what is the first case that we will be looking at? It's this one where we have 4 electrodes, 2 with fixed values, and we have only one design parameter that defines this electrode current. Note that the other electrode has this value given by the Kirchhoff law that requires that the sum of all the currents to be 0. Then performing optimization, we get this value for Xi, which is 1, meaning that we have inlets on the right here, the current gets into the body here and flows on the direction of the positive values here. Here we have outlets. So here I am presenting you the expected information gain as a function of Xi. We can see that we have a non-convex problem here, and that for this starting point we are able to converge to the true optimum here. However, if we were on the left side of this valley here, we would not converge to the true optimum. We will converge to the other setup. So that is a limitation of local search methods. We have to be aware that to get the true optimum we need to start from various points, different points. And here I am presenting you some PDFs, the prior, denoted as in gray, and the posterior before optimization on this red dot here, which is quite not concentrated. We have a bad experiment here, and after performing optimization we got this much more concentrated posterior, meaning that we can get much more information about our experiment. Now let's look at a second case where we have 3 electrodes and we have 2 design parameters. So we have these 2 top electrodes to be defined, and we have this third electrode satisfying the Kirchhoff law. Here we converge to a configuration where we have one inlet here on the bottom and one outlet on the top, and we have one electrode with 0 current. So here I am presenting you the expected information gain as a function of Xi1 and Xi2 as contours. And I'm showing you 2 guesses, 2 starting points, and how we converge to the optimum. Note that here denoted in blue we have the regions where the Kirchhoff law constraints are violated, and we impose these as constraints, so we were able to get to the real optimum. Note that we have some kind of symmetry here, a diagonal symmetry, due to the symmetry that we have on our body here in our problem. And these 2 solutions that we got are somehow related. They're mirrored solutions. Now here I am presenting you PDFs for the 2 guesses, the first guess and the second guess, where we have the same prior but we have different posteriors before optimization. But since the solutions were equivalent, the optima that we get, they have very similar posterior distribution in blue here. So our last case is one where we have 10 electrodes and 10 design parameters, one for each electrode. We are starting with a guess that we have inlets on the bottom and outlets on the top. So it's interesting that we converge to a configuration setup where we have inlets on the right and outlets on the left. Note that one could naively guess that we would converge to a situation where we have -1s on the bottom and 1s on the top. However, that would be far from being the optimal solution, since we would get an expected information gain on that situation of 2.95, when actually with this optimal configuration that we have here, we get 7.18. Much more information is gathered with this setup, which it's interesting to note how important it is to actually perform this kind of optimization, because many times it's not trivial to get the best setup for experiments, and we might do guesses that are not as good as the optimum. So here I am presenting you the posterior for this case, before optimization in red and after optimization in blue. You can see that we get a lot of information. We have a very concentrated posterior. And here I am presenting you the conversions to the optimum of Xi, where we can see that we were required to perform less than 50 iterations to get to the solution of this 10-dimensional problem. So finally, in this work we derived these estimators for the gradient of the expected information gain to be used with stochastic gradient methods. We used state-of-the-art techniques of stochastic gradient descent methods, Polyak-Rupert averaging, Nesterov acceleration, and the restart technique in optimal experimental design. And we validated our framework with numerical examples in which we got good results with small costs. So now I will present the references that were used throughout this presentation. Thank you very much for your attention.